So in this video, I'm going to be explaining how to find the initial flow rates and the time variation of fluid heights for two spherical tanks, in which the first one has some flow going in. They are connected by a tube, and the flow through that tube will be indicated by Q12. The second tank has some flow going in called Q2N, and also has a tube which Q2 will represent the flow out of that tube. So first of all, one thing to note is, so let's say these are perfect spheres. They're not drawn as perfect spheres, but let's assume they are. So we have this radius here of the first sphere. This line right here is also a radius. So if we draw a line here, let's say this is a flat line, it makes a right angle. So this HT over here is the height of the liquid at some given time, because as time goes by, the level of the fluid will fluctuate. So this vertical line is equivalent to HT, which is the height at a given time, minus R, because from here to here is the radius. And up here, as the fluid time goes on, the radius of how far the fluid goes over also depends on time, so we will call that RT. So I will draw an enlarged picture of what is in this box. So this is what is in the box. We have the radius R, which doesn't change, RT, HT minus R. So you may notice that this is a right angle, which means it's a right triangle. So therefore, we can apply the Pythagorean theorem to the triangle. So we will get R squared equals RT squared plus HT minus R all squared. And this just comes from C squared, being C being the hypotenuse, and A equals A squared plus B squared being the legs. So now what we want is the radius depending on time. So we can rewrite this by subtracting HT minus R from the left side. So what we can end up getting is RT squared equals R squared minus HT minus R squared. So then, this is important for finding the cross-sectional area of the sphere. So we can say the cross-sectional area is pi times the radius depending on time squared, which is this ever-changing radius depending on time. So what we can do is substitute this in for RT. So what we'll end up getting is the cross-sectional area equals pi times so we'll get pi times the radius squared minus HT, height at a given time, minus R, all squared. So we will use this later. For now, I'm going to erase it so I have room. So what is next to note? So the flow rate equals the area times the velocity. So using that, we can say Q12, which is of this tube here, connecting the two, equals A12, which is the area, times the flow velocity of the liquid through here. And similarly, we can say a similar thing for the tube exiting 2. So we can say Q2 equals A2 times V2. And those are just simple flow rate equations, and just specifically for each tube. So those we'll come back to those later. So let's say we have 2 points and a tube flowing out. So if we were to solve this, it's not equals. So we have this equation in relation to these 2 points, just in some container. So one important thing to note is they are on the same level. So therefore, this is 0. There is no V1, so this is 0. So then this can further be derived to this equation, in which P is pressure, I forgot to mention that, and rho is density, and G is like the gravity acceleration of gravity. So you may ask, why are we driving this seemingly random equation? Well, that's because we want this velocity. So what we will do is solve this for the velocity. And get the velocity equals the square root of GH. So now we know the velocity, and we know Q equals the area times the velocity. So now we can plug this velocity into each of those flow rate equations. So now for Q12, we will now have, it's still the area of 1, 2, but now we will plug in for the velocity. And we'll have square root of 2g h2 minus h1, absolute value. And an important thing to note for this, I'll do Q21 soon, but since h2 minus h1 are absolute values, you can't have a negative in the square root, which is good, which is what we want. But for Q2, we don't have to worry about that because we only have one height to worry about, which is the height of 2. So now we have everything we need to solve for the initial flow rates. So the initial flow rates can be written as dv dv1 dt for the first one. And what we will pretty much be doing is calculating what's going in, subtracting what's going out. So we will have Q1 in minus Q12. And this is because the only thing that's going in is this Q1 in, which is why there's an arrow for it going in. And the only thing coming out is the liquid right here. I'm going to go ahead and draw that one for there too. So now we solved for what Q12 was earlier. Well, just low big O. So we can now plug that in. So we will have A12 times the square root of 2G H1 minus H2. Now, something we need to account for is not every single time 1 will be bigger than 2, 1 may be smaller than 2. So what we need to do is, I forgot this in parentheses, is account for the sign change. So I'm going to rewrite this end part once more. So we're going to have still Q1 in, that doesn't change. But now we are going to account for the sign change. And we're still going to be multiplying by A12, and everything else stays the same. And again, this is just to account for the sign change on which is bigger and which is smaller, because just leaving it in the radical or square root, whatever you want to call it, it will always be positive, so it doesn't account for it by itself. So this is the flow rate for initial flow rate for dv1 dt, which is for the first container. So now we will do it for the second one right here. So to signify this is the second one, I'm just going to write it 2 here. And we are going to account for everything going in, which is Q2 and Q1, 2. So we'll have Q2 in plus Q1, 2. And the only thing leaving is this Q2, so we will have minus Q2. So we're going to have a similar situation in which we solve for each of these, well, Q1, 2, and Q2. We already solved for Q1, 2 just in the last one for this, so we know what that is. But now we will also have Q2. So what we'll end up having So this right here is just Q12. We already went over that. Sine H1 minus H2. Area of 1, 2, which is area of this. 2G H times quantity H1 minus H2. And I'm going to write the extended version of Q2 below it because I'm about to run out of room over here. So we will have minus, because it's exiting, it's minus. And we will just have minus A2, which is the area, times square root or radical 2GH2. So that is solving for this entire thing is the initial flow rate for 2. So now we have answered the first question, which was what were the initial flow rates for each sphere. So now it's time to solve for the height variation due to time. So this HT, in other words, is something we are accounting for. So one thing to note is I kind of smeared it. Is that dvdt equals cross-sectional area times dhdt, and this dh is pretty much what we want. So we are going to solve this equation for dh. So dh will equal the dvdt being divided by the cross-sectional area. Well, this dvdt is just the initial flow rates, which we just solved for each of the things. So each spherical container will have their own dH value, and what we just solved for, we'll just plug in here and have the cross-sectional area. So for instance, dH1 dt, which is for spherical container 1, will be, this is going to be a lot. So I'm going to need some time to write. So here was the expression for the flow rate, initial flow rate of the first two. Now we will have the cross-sectional area, which we solve for in the very beginning, which is our pi times r squared minus h minus r squared. So this is the time variation of the fluid height, in which we have the flow in minus sine h1 minus h2, which accounts for which container is taller and larger. times area of 1, 2, which is this, times square root 2g h1 minus h2. And again, this is just the initial flow rate of what we just solved for. And in the denominator, we have pi times r squared minus h minus r squared, in which we solve for this at the very beginning is one of the first things we solve for, and we just plugged in here. So that is for the first sphere. Now the second sphere will be very similar. So the second sphere will pretty much be the exact same, except we're just going to put a plus sign here because the flow rate's going in. And at the very end over here, we will have a minus sign. I may run over, I might need to write smaller. So in the numerator, we just have the initial flow rate for the second one. This is not Q1, this is Q2. I gotta change that. I just kept the last one with it, so I won't have to spend as much time writing and erasing. So we have Q2 in, we have sine h1 minus h2 accounting for which one's taller and higher, of area of 1, 2, 2g h1 minus h2. Those two are plus because they're going in. And this is Q2 going out. So this is the initial flow rate. And here we just have the cross-sectional area, which is pi r squared minus h minus r all squared. So this is the time variation of the heights for the second container. So now we have answered all of our questions, which were what the initial flow rates were and height variation due to the time variation.